Hello, everybody. Afternoon. Let's see. What got going on today? Here are the usual things. Oops, that's not the usual thing. Grabbed the wrong thing. Here are the usual things. I should grab it off. Yeah. Hopefully you all are doing all right. I saw that Rademacher students have an exam today. I looked at his exam. It looks pretty reasonable. I think all the questions are pretty straightforwardly asked. Yeah, the last question, the probability question on his test, 5A, looks a lot like his homework question. So I think everyone should be able to make a reasonable attempt at the test. So I don't know when you have to do it by and see what it said on there. Yeah. So hopefully it goes well and you guys get it done. Sorry. What should we talk about today? What do you guys have questions about? I see that, sorry, I guess ask a question, I keep talking. I also saw that he started talking about double integrals, which we have certainly already talked about. We could do more of that, although I don't imagine that's really kind of what's on your mind at the moment. Sorry, that's Rodriguez. No, that was Rademacher talking about double integrals. And Rodriguez started talking about probability stuff in general. Yeah, combinations, okay. So we can continue doing that. I don't know. It's the problem with these combination questions is it's hard to like. It can be challenging to feel like you're coming up with original questions. Let me give you guys the attendance again here. Also, a reminder, just in general, we have. Oh my God, sorry, it's Friday, my brain. Monday, we don't have class. It's a holiday. So I hope you have a nice, long 3-day weekend doing all sorts of things. I hope you guys have a chance to relax, and hopefully for those of you taking a midterm, that it's not too onerous. Rodriguez mentioned he won't ask about poker-related questions on the homework and final. Okay, that's especially interesting because he definitely did a lot of poker examples. I mean, at least a few in his notes here. So, I mean, that's, I guess, good. I don't know. I do feel like the poker ones can be kind of challenging. I don't know. The poker ones just feel weird sometimes. You have to know what all the things mean. I feel like, let me see, I had some examples here. Sorry, I know I was, so I'm sorry, my brain's getting a little like, I'm trying to remember which problems I did with you guys and which problems I did with my stats class the other day. So it's hard to remember what I've done with everybody. So let's take a look at, sorry. So let's continue talking about conditional probability because that is something that is important. So I'm going to give you guys an example that I know is pretty standard. I don't know if you'll actually be covering it, although I feel like most classes, most 17C classes usually do. Which I think I said last class I would talk about this, so I should keep my word and do the things I say I'm going to do. So let's talk about. This is an example of Bayes' rule. And let's see. let's just see if I have specific numbers here or if I need to make stuff up. Okay, here's a perfectly fine one. So here is what we've got. Chromatic analysis, CA, is used to determine whether a person has naturally blue hair. Yes, this is rather pointless. So chromatic analysis, 95% of the time correctly identifies blue hair in people who actually have it. So the way I would write this with our probability notation is the probability of a positive test, given that the person has blue hair, is 0.95. It also says, unfortunately, the test is not perfect, and 15% of the time it gives a false positive for people who do not have blue hair. So 15% of the time there's a false positive. That is the probability of a positive test given that they don't have blue hair is 0.15. And the way we are going to write that they don't have blue hair, if we're using B to represent having blue hair, we're going to use B with a superscript C for B complement, meaning everything that is not B. So B is having blue hair, and B complement is not having blue hair. And that should take care of everything, right? When you're talking about a thing and its complement, those should comprise all of the possible things that can happen. You either have blue hair or you don't, right? There's no other choice. So then we want to ask some questions. Also, sorry, one more piece of information. Research has shown, although I don't think this is really true, we're making things up here. Research has shown an actual occurrence of blue hair in a certain population is 1 in 200. Okay, so we want to use this to find the probability that someone will test with a positive result. So first thing I want to know is, what's the probability of a positive result? And so there's two different ways someone can get a positive result. They can either have blue hair and get a positive result, or they can not have blue hair and get a positive result. And so we have to kind of write all the ways this can happen. And this is, again, an example of what's called the rule of total probability. So I like to draw a tree for this because I feel like it makes sense. So, and the tree kind of is like it's like a decision tree, I guess you could call it, where at the first step you have to decide, okay, well, there's one or two things that can happen. You can either have blue hair or not have blue hair. And it doesn't make sense to think about the test first, right? You don't say you have a positive test or a negative test. You say the kind of the independent thing, I guess. So you can either have blue hair or you cannot have blue hair. And the probability of having blue hair, well, research has shown an actual occurrence of blue hair is 1 out of 200. So the probability of having blue hair is 1 out of 200, which is 0.5% or 0.005. That's not 0.5%. Is that 0.5%? Yeah, that's 0.5%. Sorry. Sometimes the math is hard. Okay, and then if the probability of actually having blue hair is 1 in 200, the probability of not having blue hair is the rest, 199 and 200, or 0.995%. I should say, sorry, 0.995 or 99.5%. And then at the next stage, you can either test positive or test negative. And so here's the thing I want you to kind of remember, right? At each stage, when you have one thing happen or the other thing happening, those two things have to add up to 100%, right? You have blue hair or you don't, adds up to 100%. If you have blue hair, you test positive or you don't, that's going to add up to 100%. So if you have blue hair, the probability of testing positive, given that you have blue hair, is 0.95. So what's the probability of testing negative, given that I have blue hair? What's it have to be? You guys are also welcome to talk. But yes, it's 0.05. I get it. Nobody wants to talk. I don't love talking either. I mean, I talk a lot, but only because I have to. And then same kind of deal down here, right? So we see here, the probability of a false positive or a positive test given that you don't have blue hair is 0.15. So this positive here is a 0.15 probability that happens, which means the negative part here has to happen with what probability?
Is it 0.85?
Yeah, thank you. Thank you. You're a real live person. Okay, so and we're trying to find the probability of getting a positive test, and we don't know if the person is actually having blue hair or not, then we just find all the ways to get to a positive test. So it's going to be this times this plus this times this. Because, and here's where the ands or ors are going to come up again, right? The probability of testing positive is the probability of having blue hair and the probability of testing positive given that you have blue hair, or the probability of not having blue hair and the probability of testing positive given that you don't have blue hair. But I really want you to hear those ors and those ands, right? The ands are corresponding to multiplication, blue hair, and testing positive given that you have blue hair. The ors correspond to multiplication. So we can have blue hair and test positive, or we can have not blue hair and test positive. And that's all the ways you can add up to being to having a positive test. Should be worth noting, this is the probability of having blue hair and testing positive. This is the probability of having not blue hair and testing positive. Right, that's what that intersection symbol means there. And then we can calculate this. So this ends up equaling 0.005 times 0.95 plus 0.995 times 0.15. And now here's what I want you guys to kind of see before we calculate this. This part isn't going to contribute very much, right? This 0.005 times 0.95, that's going to be pretty small. Whereas this is almost 1 times 0.15. So what we're going to expect is that we're going to have the likelihood of testing positive being 15%, close to it. But not because 15% of the people have blue hair, but because 15% of the people that don't have blue hair test positive. And that's kind of the overwhelming majority of the positive tests. So that's what's happening here. Let's see what we actually get. We need a calculator. So let's see if I have 0.005 times 95, sorry, 0.95 plus 0.995 times 0.15, we're going to be getting 0.154. So 15.4% of the population would be testing positive. Most of those coming from false positives, a few of those coming from actual real positives. Okay, so this isn't the base formula part yet, but the base formula part's next, which again, I think is something you guys will talk about, but even if it's not, it's something you should know about. some of you might have to take a stats class at some point. You'll definitely talk about it then, whether it's stats 13 or stats 100 or some other stats class. It's good to know about. Yeah. So, so just 1 second. So we're at this. So they're laying down pavers in my yard, which is great because eventually in a couple of weeks I'm going to have a yard that I can actually live in. But right now they are cutting them and it is really loud. So let me put on my headphones and do that. Okay, I should be connected. So somebody say something. Oh shoot! It just. Sorry, it did something. It's connected to my wife's phone because it's. No, it says it's connected here. I don't hear anybody though. Tracy, can you say a few words? Oh, say something.
How was your day?
Good. Cool.
Okay.
My day was good. Then I can hear you, which is what matters. Yes. Okay. So yeah, it's really loud out there. So the question you can then ask after you've done something like this is, you say, okay, what's probably positive, and you know probably having a positive test, given that you have blue hair, is equal to what we said 0.95. The question we're often interested in, right? Because usually you don't know that it's given that someone has blue hair or not. Or a better example, which we'll do in a second here, is like whether or not you actually have a disease. So I want to know not what the probability of having a positive test given that I have blue hair is. I want to know what's the probability that I have blue hair given that there was a positive test, right? Because I know the test result. I take this test, I get a test result, and maybe I don't know my hair color because I've never looked in the mirror. But the probability of having, although at this point I could probably just look at my hair because you know it's super long. But the probability of having blue hair, given that I have a positive test, is going to work like this. Well, again, this is a conditional probability. So it's the probability of having blue hair and a positive test divided by the probability of having a positive test. Now we actually already know both of these, but let's write them out anyway. So on the bottom, we have the total probability. So the probability of having blue hair and a positive test, or having blue hair, sorry, not blue hair, and a positive test. But then this thing here, right, the probability of having blue hair and a positive test is the probability of having blue hair times the probability of a positive test given that you have blue hair. And then the same stuff on the bottom. Probability of blue hair times the probability of test positive test given blue hair, plus the probability of not having blue hair times the probability of a positive test given that you don't have blue hair. And this formula comes up quite often. So this is Bayes' formula, where if you're trying to find the probability of some conditional probability, you can use the reverse direction conditional probability to figure it out. And so in this case, we already know what most of this is. I'm going to go back to this after just 1 second. I'll come right back. I know that this thing here, that's just this divided by all of this. So it's the probability of having blue hair was 0.005. Probability of positive test given blue hair was 0.95. That same thing goes right here, right? This and this are the same. Plus, this was the probability of not having blue hair was 0.995. And the probability of a positive test given if you have not blue hair was 0.15. So our denominator is just 0.154. That's what we got from the last work. And the numerator is 0.005 times 0.95. It's 0.00475. When we divide these, we get 0.030, no, let's just say 0.03. Approximately 0.03. So here's what this means. It means given if someone has a positive test, the probability that they actually have blue hair is 3%. Very different than the probability of a positive test given that you have blue hair, right? If I have blue hair, the probability of having a positive test is 95%. If I have a positive test, the probability of actually having blue hair is 3%. So it's really kind of important to understand that although those things kind of sound the same, they're in fact extremely different. So are there questions about this? I definitely want to do another example, but are there questions? Yeah, Teresa.
So for the first part we did, which was the percent, that one was the probability of testing positive for blue hair, basically.
So the way I would like, so you mean this one right here?
Mm-hmm.
The way you should read this is it's the probability of testing positive given that you have blue hair.
Okay.
It's basically the accuracy of the test, right? If you have blue hair, 95% of the time, a person will test positive.
So it's test positive given have blue hair?
Correct, right? And so that's how we read this, right? Because the second thing is always the given thing in this notation.
Okay.
Okay. And so I should mention, although Bayes' formula is perfectly fine, you don't actually need to know Bayes' formula by heart. Like, and to be honest, I probably don't know it by heart. I probably just kind of derive it each time I use it because the process of deriving it using a tree is kind of more helpful anyway. Let's look at another very similar example. I know, so for me, actually, there's one thing I want to look for real quick because I know one thing. Nope, that's not it. Sorry, one second. I know I have this other example that I would like to use if it's available. Just one second. Okay, sure. So let's look at this one. So I will first of all warn you, this is going to feel very much the same, right? The next, like the idea of using Bayes' formula is kind of the same each time. Although there are ways to kind of make it a little bit different. So let's look at this example. A rare disease affects 3 in 10,000 people on average. A blood test for the disease All right, I think I can turn off my headphones. I think sorry, the headphones. I don't love wearing headphones. No, it's still pretty loud out there. Wow, I'm really talking really loud, but I can't hear it because headphones. A blood test for the disease is positive in 99% of the cases. Okay, so just let's stop for a second here. If I say that D is having the disease, and plus is a positive test, then what we're saying that this is the probability of a positive test given to have the disease is 99%. That's what that statement is saying there. Okay. Also, in the 2%. Sorry, words. Also, the blood test has a 2% false positive. So what am I saying with that? What conditional probability is equal to 2%? The probability of I'm saying I have a false positive. I'm saying I have, what should I have here if it's a false positive? It's a false positive. Oh, you're so close, Teresa. So what you're saying there is you're saying that's the probability. In fact, that's the question that we're going to answer eventually. Is the probability of having the disease given that you have a positive test. But if I have a false positive, does that mean I have? So if it's a false positive, do I have the disease or not? No. So I need to write that as I don't have the disease, which is the D complement. So it's the probability of a positive test given that we do not have the disease. So that's our false positive. Okay. So then we want to ask, and actually that's the question we want to ask. We want to ask the question, if I test positive, what's the probability that I actually have the disease? Okay. And what we see a lot of the time with these kinds of questions, it's not always the case, but a lot of the time it adheres more to just like, what's the actual population percentage? It's probably going to be pretty likely that it's going to be close to just what the percent of the population that has the disease is. So I want to find the probability of having the disease given that I tested positive. And the way I'm really going to think about this is it's the probability of having the disease and testing positive divided by the probability of testing positive. And I don't think I need to write out the rest of this formula, not because I wouldn't, but because I think it's easier to use a tree. I mean, it's really the same work. Let's use a tree. So you have a person, and they either have the disease or they don't. And the probability of having the disease is 3 in 10,000, which is 0.0003, right? 3 in 10, 100, yeah, 0.0003. And the probability of not having a disease is going to be then the rest, 0.9997. Then you can either test positive or test negative. And we know what happens. Given that I have the disease, the probability of a positive test given that I have the disease is 99%. Which means the probability of having a negative test given that I have the disease is gotta be 1%. Right? If I have the disease, I either have a positive test 99% of the time, or I have a negative test 1% of the time, right? That's all that's the only thing can happen. Similarly, if I don't have the disease, there's a 2% chance, which is 0.02, is a 2% chance of a false positive, which means there is a 98% chance of an accurate negative test. So now, what's the probability of having the disease given that I have a positive test? Well, the positive test, let's see, how do I have a positive test? It's going to be this and then this, right? So I'm really just taking all the paths, right? The path to a positive test is this. So that's this times this. Plus the other path to a positive test, which is this. 0.9997 times 0.02. On top, we have the probability of having the disease and a positive test. And that is just this path here, right? That's the only path where I have the disease and have a positive test. That's going to be the 0.0003 times the 0.99. So let's see, calculating this with 0.0003 times 0.99, which is small, it's 0.000297, which is not surprising, right? It should be really, really close to 0.0003 because it's like 0.0003 times 1 almost. And then divided by the same thing, whoops, plus 0.9997 times 0.02. We get about 0.014. Pen, where'd my pen go? So again, what this says is that even though the probability of having a positive test, given that you have the disease, is 99%, the probability of having the disease, given that you have a positive test, is 1.4%, or 0.014. So really, really different. It's important to know, right? So that means like if you're being tested for a disease that is not very prevalent in the world, it might be a lot more likely that you've actually gotten a false positive than you actually have the disease. That's why they usually test again if you test positive for something. They're like, well, maybe you're just one of those people that got a false positive. So now let's actually ask one more question with this because it's kind of interesting. Let's say the person tests positive twice, right? They tested positive once. They're like, well, maybe it's a false positive. Let's test positive again. Let's test again and see. So let's let 2D be 2, or 2, I'm just writing this. So let's let plus be 2 positive tests. We're trying to find the probability of having the disease given 2 positive tests. Okay, so we're going to do the same sort of thing. I want to know, again, really it's the probability of having the disease and having 2 positive tests. Oh, we should also, I should say, we're making the assumption that the tests are independent, right? Having one test and having another test, their outcomes don't depend on each other. They're wholly independent of each other. So we're looking for the probability of the disease having 2 positive tests divided by the probability of having 2 positive tests. All right, we're going to make a tree again. It's going to be slightly different, but still pretty much the same. So I either have the disease or I don't. And we know the probability of having the disease is 3 in 10,000, which is 0.0003. And the probability of not having the disease is 0.9997. And then we can, now No, I think it just makes sense to think of it this way. You can have 2 positive tests. Huh, that's interesting. So I'm looking at old notes that I've actually looked at before. Like, okay, yeah, that's fine. I only really care about the positive tests, so I'm just going to see, well, what's the problem with having 2 positive tests? Well, it'd be 0.99 times 0.99. There's also, right, you could have other things. You could have positive, negative. You could also have negative, positive, although if you got 1 negative test, you probably wouldn't take a second test. And you could also have negative, negative. And these other things would add up to the rest. Really, what people also do is they're like, okay, well, at this stage, I could have a positive or a negative, and then at this stage, I could have a positive or a negative. And this is the only way to get to 2 positive tests, which is a 0.99 and then another 0.99. And then same kind of deal here. You can have a positive or a negative, and then we can have a positive or a negative. We only care about the ways of getting 2 positives. Oh, which I guess I should have written that's a probability. Probably here. Probably a false positive is 0.15. 0.15? That doesn't sound right. It was 0.02. And it's also 0.02 here. All right, so probability of having 2 positive tests, or I should say, the probability, well, actually, no, that's a good question. The probability of having 2 positive tests is this path plus this path. So it's 0.0003 times 0.99 times 0.99, or 0.99 squared. The probability of having 2 positive tests this way, when you don't have a disease, is 0.9997 times 0.02 times 0.02. I think they've actually stopped. I'm going to take these headphones off. They're killing me. Yeah, good enough. Let me turn these off. Okay. Yeah. All right, cool. So I can yell at you more. And then this probability up here, the probability of having the disease and 2 positive tests is just this path here. So it's 0.0003 times 0.99 squared. You will start to notice when you do, if you do these, that you always get this top part here, and then that top part shows up again as part of the bottom, the denominator. I've noticed that often. So here, calculating this, let's see. We get 0.0003 squared times 0.99. Sorry, that's wrong. 0.0003 times 0.99 squared, which is 0.00029, okay? And then divided by the same thing, plus 0.9997 times 0.02 squared, which ended up being much higher, 0.4237. Right, so probability of having the disease given 1 positive test, 1.4%. Probability of having the disease given 2 positive tests, 42%. So there's a much more likely chance that, and which makes sense, right? You would imagine you have a much higher chance of having the disease if you actually tested positive twice. Okay. What else? What else would you guys like me to say in these last 10 minutes? Actually, so while you think about that, let me again give you the attendance just in case you haven't done it already. There's also the, oh, I know what sorry, I thought I had another link in here. Let me grab the other link that I wanted to make sure you all have. 1 second. Sorry, 1 second. here's actually what I want to do. So here is the link to the attendance and the tutoring. There's also a link to the fall quarter evaluation. If you guys, so it's available until the end of fall. Why fall? Wow. Have I said that every time? This is not fall. This is spring. Wow. Jeez. Okay. Here's a link to the spring quarter evaluation. I've been saying fall quarter, like I've got all these like places I've typed it and it says fall quarter in every place I've typed it. Here's a link to the spring quarter evaluation. If you guys could please fill it out when you have a chance, I would greatly appreciate it, as would Sarah and other people I work for. Yeah, that's smooth. Thank you for filling it out already. I appreciate it. Yeah, fall quarter. Fall is a ways away. Okay, so I'm kind of feeling like I've run out of things to say, unless you guys have specific questions you want me to address. I think I might end class early. I know that's a crime, but not really. I'm just kidding. Unless you guys want to tell me about how you're doing, what's going on in your lives.
Wait, so I have a question about the situation with probability. When
Sure.
we write the notation with probability and we put in the two conditions, how we the order of how we write the conditions and it matters, correct? Or okay.
So that whenever you're writing a conditional probability where you have that little vertical line in the middle, it's always the second thing that is the known piece of information.
Okay.
Right. So you're saying, oh, the probability that James gets his haircut, given that we are in quarantine for 5 more months, would be really high, because the given information is the second thing, right? So the probability of haircut first, vertical line, 5 months in quarantine, right? That's how you would write that. So it's always the second piece of information is the known thing. And I feel both of you, Felicity and Jennifer, I feel you. I imagine none of you are planning on taking math over the summer, because I imagine for most of you, this is your last math class. That said, the AATC also offers help in chemistry and physics. So if those are things that you have to take at some point, you should definitely talk to Jade, or I'm pretty sure Maria will be back for the summer. She just had a baby like a week or 2 ago.
Oh, congrats to her.
But I imagine she'll be back as soon as she's allowed to be, and Jade will be around, and Duff can help with physics. So you should definitely, if you're doing stuff over the summer, there are people who have office hours, but I don't think there's, actually I don't know, there might be co-classes for chemistry. I don't know. I don't think there are, but definitely in fall there will be co-classes as usual. So, well, maybe not as usual, but there'll be co-classes online.
Is there co-classes for stats? I think I might take that later next year. Not fall quarter though.
Okay, yeah. So typically I would say typically we haven't offered co-stats in the past, just because we have limited kind of span. But we definitely, so I imagine you guys know, maybe you don't. I've been teaching a co-stats class this quarter, and we're not teaching one in the fall because fall is usually our busiest quarter. We have a lot more classes to teach in the fall. But I imagine we will definitely be able to offer co-stats in the spring, possibly in the winter. Depending on the class you take, the class that I've been teaching this quarter has been co-stats 13. But I hope to expand that to being able to help with stats 100. But Sarah is also, first of all, Sarah usually has more availability for online appointments than I do. So you can actually make an appointment with Sarah in general. And she definitely can help with stats 100 and also stats 13. And maybe other stats classes too. So generally, yes, there will be stats support. Also, the student tutors there are student tutors that do help with statistics in addition to all the math classes. So there will be some form of support one way or another. You guys have other questions in general?
That's your cat.
My cat is not in the room right now. Usually she's not allowed in while I'm teaching. She's being really persistent. Yeah, things are all right. Let me actually let me show you guys if I can. One sec. I know I have this here. How do I do this thing? Oh, I think that's my desktop. You know, like when you want to be smart and you can't because you're dumb.
I do that every day.
Yeah. Oh, I see it. Here we go. How do I put this in the chat? I have a picture of my backyard. Did I want to? Oh, I can just share my screen. How about that? Super smart. Here's the work that's happening in my backyard. Lots of stuff. There's a lot more now. Like they've done all of this around the side. So it's exciting, but obviously very noisy. That's what's going on in my life. Anyway, I won't bore you guys anymore. But feel free to, no class on Monday, as I'm sure you're all aware. For those of you taking the Rademacher midterm, you're certainly welcome to ask questions, although I really feel like the midterm's pretty straightforward. Like the questions, I think he explains what he wants from you very nicely. So for those of you taking his midterm, I don't think it's going to be too bad. But if you have questions, I can offer you very, very little guidance, but maybe a tiny bit if you have a question. But really, I think we've talked a lot about those types of questions in class. So you might be worth going back and looking at some of the videos if you're getting stuck on something. Yeah, I agree with Teresa. I'm wishing you all the best as well. All right, I'm going to end class, but if you guys have questions, don't hesitate to send me an email or write a discussion. You're welcome. Talk to you guys on Wednesday of next week, not Monday. All right.
Thank you.
You're welcome. Bye.